Okay. So, yeah, you can hear me, right? So essentially the idea is, okay, one point I would like to mention here where we dropped off yesterday is to identify why or what this portion of the circuit is doing, right? This portion is nothing but, what is it? If you see the voltage, let's not get confused with from where the feedback is taken and all that, right? But if you see the voltage that this amplifier with a gain 1 is amplifying, or rather it's working as a buffer, right? What is the voltage that is going as an input to this guy? So if you see the voltage that is going as an input to this guy is the voltage across this resistor RC, right? If you carefully look at the connection, this terminal is nothing but this terminal, and this guy is nothing but this guy, right? So all what we are doing using this scheme is we are just measuring the voltage across the resistor RC. So the second amplifier does nothing but just it acts as a buffer, so that when we will be measuring the voltage, output voltage V0, right? There will be some loading on V0. So we want to ensure that the loading, because of the readout circuitry, does not kind of mess up with this bridge arrangement by itself, right? That's the reason we kind of use a separate buffer to isolate the readout circuitry from the bridge arrangement. So that is the requirement. I mean, that is the reason why the second buffer is there in the first place, right? And going to the point that is actually an important point when you are actually what Shubham is raising, that what if the values are way off, right? So that you will see even when you are doing forget the sensor wherein this guy is actually sitting outside, right? Even when we are designing this integrated circuits wherein there will be local feedback and everything will be inside the chip, right? Even there, when you start designing, if you see scenarios that or if you choose elements, values which are like kind of far from each other, right? You may not be even able to stabilize the circuit, in the sense that either it will saturate or it will keep oscillating. So you can assume, or it's fair to say that the value of RC and the value of RW, right, should be close enough, right? And only thing that will happen is only the small variations of RW which would have happened because of temperature variations. In this case, there is no temperature variation, and that is what we are trying to kind of ensure, right? That because of the flow of the fluid across the sensor, right, the temperature will vary, right? So and we know what is the range of velocity that we are expected to measure. So from that range, we know what can be the maximum and minimum temperature variation that this sensor wire would have experienced had there been no feedback, right? So once we know that range of variation, right, then it kind of becomes easy, in the sense that we'll choose the value of RC somewhere right in the center of that variation, small variation, right, that will happen, and then use this feedback to ensure that RW kind of remains constant with RC, right? So let's look at the equilibrium equation which we actually did for the constant current anemometer also. So here if you see, I is a variable, right? And UV of course is a variable which we had discussed, but then RW is not a variable anymore, TW is not a variable anymore compared to what we saw in the constant current anemometer, right? And also because the temperature TW is not varying, right? RW, this is anyway a constant. We are ensuring in this mechanism, what we said is we are ensuring RW we are maintaining equal to RC, and RC is a constant. It does not change much with another thing to understand, right? RC also, we should not lose sight of the fact that RC also is a resistor. This also has a dependence on temperature on itself, right? So while we say that the current is varying, right, but the current variation itself should not mess up the value of RC itself, right? So again, going back to the point that Subham was saying, that if I itself varies a lot, we take it from like to ensure that RW kind of comes close to RC, the range of I itself becomes so large that RC itself also will start getting impacted, right? With a large variation in I, there will be a temperature variation in RC. So that we have to avoid. So here we are assuming that, you know, these are all properly chosen around an operating point, and the small variations are sufficient to realize RC equal to RW, and the current is kind of well managed without saturating this GM stage, right? So from here, these are all, if you see, there is no variable here as such. So if we just rearrange and write TW, this is how it will look like, okay? And then putting TW now back in this equation, that's all what we have done. This guy goes here. What we see is, and UV, we know, UV we had seen what is UV, right? This is UV, we have discussed this. So based on this, what do we see now? We see I square is now proportional to root of the velocity of the fluid, right? So if now this is I square now, and the output voltage, what is the output voltage? That is nothing but I multiplied by RC, because this is the voltage we are sensing out, right? Assuming that most of the current kind of flows here, very little current flows here. So this KR has to be way, way higher. So now if I replace this guy in this equation, very simple, right? I mean, I is just replacing I with V0, right? So then we come up with an expression where the output voltage, the square of the output voltage is proportional to the root of the velocity of the fluid. Please note, everything else now is a constant in this. Compared to, if you compare this to what we had in the constant current anemometer, right? So if you see here, yes, in the constant current anemometer, what did we have? The output voltage was proportional to the square root of the velocity of the fluid, all right. But then we also had another variable, the temperature of the wire itself, that was varying, right? So if you see here, this also did the job from a very high level, if we think, right? This also did the job of measuring the fluid velocity. And when we are talking of fluid velocity, we are talking of the absolute velocity, right? However, it had an added dependency on the temperature of the wire itself, which is, which is an unknown, or we need to probably have a scheme to measure the temperature of the wire itself, right? Which is again an added complexity. Why to again measure the temperature of the wire and all that, right? However, the constant temperature anemometer scheme, using the feedback, what we have ensured is the temperature, the variation in the temperature wire, that is taken out, and we are left with, so these are all constant, and we are left with only the velocity of the fluid to measure, right? Does it make sense? Now, again, the same equation I have copied here. So if I rearrange the terms little bit in a way which is simpler, so we come up with an expression where the output voltage is proportional to the square root, and then of course we have a half to the power half coming here. And what is C? C is nothing but the output voltage at V equal to 0, right, when the fluid velocity is 0. And what is gamma? Gamma is this constant. We know all the values of this constant. We know RC, we know J, B, A, all of these are known to us, right? So these will be subscripts. So yeah, so all of these are known to us. And based on that, if we actually plot the output voltage as a function of velocity, it will look somewhat like this. Any observations? Any thought? So the thing is, if you look at from a measurement of the velocity, the absolute velocity, right? Of course, it is not a linear relation, right? That is evident. It's not a linear relation. So when we are talking of let's say small signal variations, if we want to measure, we know that the fluid velocity will be, let's say, 4 meters per second, let's say, right? So somewhere here. So we will try to, ensure the operating point of the sensor system is such that, it falls, the the operating point falls at a point such that around this operating point we can assume this to be a linear system. So for example, this place may not be a good point to do the same assumption, right? So choosing the right biasing condition. So similarly, somewhere here may be still a right, if you look at the, if you look at the curve, so this point can be a good place to make an assumption of you know assuming that around this we will have a linear kind of a behavior, right? Okay, so now let us try to make the small signal. We looked at the large, how the large signal is going to look like. Now let us try to make a model of the, let's try to make the transfer function, the small signal transfer function of the anemometer system, right? So please note that this portion we had already seen while discussing the constant current anemometer. I had mentioned to you that it is an open loop system and it has a lot of disadvantages. But then why did we study that in the first place? And I had mentioned to you that, look, we have studied that in the first place because we wanted to come up with transfer function of the sensor wire, and that we will be using somewhere else, and that somewhere else is nothing but in the constant anemometer system. So this portion derivation we have seen in the previous slides, in the previous lectures. Now it's clear, right? This, do you want me to revisit? I hope you don't want me to revisit this portion. This was discussed, I think, a couple of classes back, right? So this is the delta RW that we would expect. So if you look at what is the input to the system here, the velocity, the fluid velocity, delta V, right? And the feedback, what does the feedback do? The IS, delta I mean the current that is flowing in the resistor, in the sensor wire resistor, that is now in a feedback loop. So in the original discussion that we did a couple of classes back, we had derived the transfer function delta RW as a function of delta V and delta I, right? And because that was constant current anemometer, we had said that the delta I will be 0, right? Here it's not constant current. Here the current is actually in feedback loop, right? And because of that, what we have here is a current is being fed back into the bridge, and this delta RW is going. Where is the delta RW sitting? How do we complete the loop? So the delta RW is a part of the bridge, right? And what is KB? We'll look at how to derive KB and what KB means. But because of the variation of the sensor wire delta RW, if we multiply this with the bridge constant KB, we will get an effective bridge output given by delta V. And what is the KB? We will look at it. But if you look at the arrangement that was shown in the previous slide, we had the Whetstone bridge arrangement, right? And then we had the feedback. Now that delta RW multiplied with the bridge constant gives a delta V. And where does the delta V go? The delta V goes as an input to the transconductance amplifier which we had, right? And that transconductance amplifier controls the current flowing into the sensor wire, right? So this part, how we are modeling this is understandable, right? And what we do is that same current, right? The same current that is going, actually I should have drawn it probably little bit, there is one, I would say, mistake here. I should show that this is I and this also is I. The same current is flowing. So probably instead of RC being shown like this, I should have shown RC like this and then measure the voltage across this, right? Because that would have been the proper right representation. But then, you know, let's, I mean, I have represented it like this, but, you know, you should not make the error to understand that the same current I that is being fed back is actually flowing into the constant resistor RC, and the second buffer amplifier that we had was actually measuring the voltage across the resistor RC, right? So this is the scheme that, I mean, this is a small signal transfer function model, block diagram, that we can kind of, this is the equivalent of what we discussed in the previous slide, right? Now we need to know what is KB. So let us look at what is KB a little bit. So let's say we have this a Whetstone bridge amplifier with a power supply Vs, with a voltage supply Vs. When we are talking of the bridge constant, right? Please note, when we are talking of the bridge constant, we are going to derive how the voltage, the output voltage of the bridge changes as a function of the change in the sensor wire. Everything else remaining constant. The supply remains constant. RC of course is constant and these guys are constant. Meaning while we are talking of the bridge constant, we are not talking of the feedback mechanism and all that, right? Because feedback mechanism is already represented in this part. That is not going to come into picture yet, right? We are interested in finding what is the bridge constant, right? So if RW varies slightly, right, from the operating point, what is the change in delta VB? If we calculate that, and then with the, I have not shown the calculation, you can do that. It's a very simple calculation. So VB, if you look at VB, right, VB is equal to half minus of RW divided by RC plus RW, right, multiplied by of course Vs, right? So now if you do delta VB, delta RW, you can do a delta VB, delta RW and express, you will get an expression as a function of RW by RC. And at the equilibrium point, when RC is equal to RW, if you solve this delta VB by delta RW, you will find the KB, the bridge constant, is given by minus Vs by 4 RC, minus Vs by 4 RC. So this 4 comes from the differentiation and with the assumption that RW is equal to RC in the equilibrium point. You can do this portion of the maths and see that whatever I'm saying is correct. You can verify this. And please note the dimension of the bridge constant, right? The dimension of the bridge constant is actually Vs by RC, which is nothing but, I can call it the bridge current or the bias current, right? Where IB is equal to Vs by 4 times RC. Minus is fine. Minus is just a polarity thing. So IB, so basically KB can, the bridge constant Kb, I can treat it as an equivalent to the bridge current, right? Multiplied by, so this current multiplied by this delta Rw gives me delta V. So dimensionally also we are fine. So Kb, the fact that Kb should have a dimension of current, that is understood and explained here, right? So, and once we have the delta V, we are passing this, I mean, we are giving this delta V as an input to the transconductance amplifier, and that changes the current in the bridge, which is what we explained. And this RC, this is little bit of an erroneous expression, I mean, representation. We can show the RC as a resistor here, or probably a block, or something like this here, to ensure, to kind of represent that it's the same current, or it's actually not an incorrect representation. You can say that the signal, the GM, the transconductance amplifier gives a signal I to the bridge, and also the same signal goes and flows to the resistor RC. So whichever way you look at it, you get a voltage output which is across the resistor RC. Okay. Now delta Rw we knew. This we knew from our constant current anemometer discussion. This expression we had with us, right? So what are we doing now? So let's replace one by one. So what is Ki times delta Is and Kv times? So Is is nothing but this guy here. So Is, I'm replacing this. I'm replacing Is by delta V0S by Rc. So this guy is replaced by this guy, right? Multiplied by Ki, and then, so this is just a replacement of delta Is in terms of delta V output. And then what is delta Rw here? This is nothing but delta V out divided by Rc divided by minus of, so delta Rw is here, right? So I'm just working backwards. I'm working backwards, delta V0 by Rc, which is the signal here, which is the current here, and this divided by Gm is the delta V, and this divided by minus Ib is my delta Rw, right? So I just work back all the way from here to here, and I'm replacing delta Rw with delta V0 divided by Ic times Gm times Rc. Is this clear? I think this should not be Ic. One second. This should not be Ic. Yeah, this is a typo here. This should be Ib. This should be Ib. So Ib times Gm times Rc. Ib is again the bridge bias current, or you can think of it as a bridge constant, right? So if I replace delta Rw with delta V, and then now I have everything in terms of delta V output voltage, delta V0, and I have delta V, which is the velocity of the fluid, right? So I have now in this expression, I have everything which needs me to relate the output voltage with the fluid velocity, right? So rearranging this term, delta V0 by delta V is the constant, K CTA, the constant temperature anemometer. This is, you can think of it as a DC gain, and then we have the time constant tau times CTA. So let's look at what is the tau. So this is the constant, K CTA, and this is the tau CTA. So tau CTA now you can see is nothing but tau V, whatever we had in our constant current anemometer, right? That tau V divided by a factor here, and this I can make it pretty large. So whereas my tau V was in the range of milliseconds, the new, again this should be there's a typo here, the new tau CTA, this should be tau CTA, the tau CTA is in the order of microseconds. So the time constant now of the constant temperature anemometer is in the order of microseconds. So we have reduced the time constant, or we have increased the response, we have improved the response time significantly from millisecond range to microsecond range, right? And another important thing is the sensor element is devoid of temperature cycling, right? And of course, here we have improved linearity because all the temperature variation and all those stuffs are not there, and there is no temperature cycling. So we had discussed in the constant current anemometer sensor arrangement, right? That because the temperature element itself, the temperature of the resistor element itself keeps varying, that has its own, that creates its own issues of not having a linear kind of a behavior. It will have probably a hysteresis loop and all that. So the temperature cycling of the sensor element is also avoided. So any questions on this, Shubham? Okay. Okay. Okay, so this is we'll quickly look at some state-of-the-art kind of anemometers. So this is from a company, I think Streamline Pro System. I think the company name can be different, but this company makes these kind of sensors. So you can see essentially these are the sensor tips, and of course we have a temperature module, as we had discussed, right? That our application might need to measure the temperature of the wire itself. So and this is a quite advanced system, right? So we will have to measure the temperature, and we'll also have a velocity module, which is what we discussed so far. And then we have a calibrator. So this is very important in general for all realistic systems that we'll end up designing. But calibration techniques are not a part of the course, but this in itself is a pretty interesting thing to understand. And then of course there are probes. There is an A to D, an analog to digital converter, which will convert the analog signal to a digital output. And then of course there will be software for data processing. So all those linearization, you saw the curve, right? It was like this, right? So probably you will have some software correction for all the errors that you will make because of the inherent non-linearity that will come into your measurement, right? So you'll have some software to correct for that. So important considerations while we are designing the state-of-the-art anemometer systems, we need to look at optimal frequency response, which means which is what we kind of discussed, right? That we have the feedback mechanism in place to ensure that it has a fast enough response, or in other words, a small thermal inertia, right? And for good spatial resolution, a short sensor length, which is much lesser than the AD size, that is important. So what we mean by spatial resolution is we need to see, when we are talking of measuring the velocity, right? We are going to say that this is the velocity at this point, right? So we have to be precise that this is the velocity of the fluid at this point. So if the resolution, if the resolution is messed up, right, we may not be able to get a right measure of the velocity at what point we are measuring. That itself may not be available to us. So we need to ensure that we have a short sensor length, which will be much lesser than the AD size. AD size is the turbulence that will be created in the fluid, right? So again, this I think needs a little bit in-depth discussion. So you are free to kind of look at it. But the point is the sensor length should be short. The sensor length should not be a long sensor length. However, if you look at the next criteria for minimum N losses, right, we need a high aspect ratio. So the length here needs to be high. The length here needs to be high. And here we are saying that the sensor length should be short, right? So there is a contradictory requirement here, which is what we need to kind of in our system that we are designing. So those are the optimizations that we will be doing. So for high sensitivity and high SNR, signal to noise ratio, and good frequency response, we will need a high temperature coefficient of the resistance that we have. So actually, if you see, right, we will probably, this is the wire across. You may not be able to see it. It may not be visible. So there is a wire across these probe tips. Okay. And for also another thing that we need to ensure that since this is going to be the probe is going to be submerged in a fluid, the metal or the chosen sensor material, we need to ensure that it doesn't undergo oxidation, because if it undergoes oxidation, it is going to reduce the sensitivity of the sensor material itself. So these are some few key important practical considerations. And so these are a zoomed in view of the miniature wire probes. So you can see we have a platinum plated tungsten kind of a probe with a 5 micrometer diameter and 1.2 millimeter length. And then we have gold plated probes with 3 millimeter total wire length, which is actually much higher. And 1.25 millimeter is the active sensor length. And then the copper ends are, we have the ends are copper, these ends are copper ends. And accurately defined sensing length, reduced heat dissipation. So these are the advantages of using these kind of wire probes. Reduced heat dissipation by the prongs, meaning you don't want the heat to be dissipated here itself, right? The heat should be concentrated here in the sensor wire itself, right? More uniform temperature distribution along the wire and less prone to interference. It should be prone. Less prone to interference to the flow measurement, right? So this is actually important when we are placing the probe, right? The flow itself of the fluid should not be disturbed. If the flow itself is getting perturbed because of the placement of the probe, right, then it defeats the purpose. So that's why the small dimensions are very important, along with ensuring high sensitivity and also reasonable durability in terms of age, right? We need to use the sensor for a long enough time. So that's why that oxidation and all that stuff comes into picture, right? We need to choose the right material, which will last longer, right? So multiple considerations. And then we have two kinds of probes. One is film probes, and the other is, probably you can say actually wires or fiber film probes. So if you look at it, right, thin films are deposited on a quartz body. The quartz layer protects the film, metal film against corrosion, wear, physical damage, and electrical action. And then there are hybrid film probes, wherein the film is deposited on a thin wire-like quartz rod, right? It's still a film, but it is deposited on a thin wire-like quartz rod, and a split fiber film probe. So these are the different types. So this is a film. You can see that, right? This is a, sorry, not, yeah. So this guy is a film, right? You can see how the film is actually deposited. And then we have different probe structures like X-wire film probes. Then we have split wire film probes for 2D flows, and then we have triaxial probes for 3D flows. So here you can see kind of a X kind of a structure, right? These are X kind of a structure. And then for 2D, so here we have for 3D flows, right? We have multiple wires in different orientation, right? So this is just to give you an idea of the complexities that are involved in modern instrumentation. That if you want to measure multi-dimensional flows, right? How the the sensor structure itself should look like, right? So yeah, so use wire probes wherever possible because it is relatively inexpensive and better frequency response can be repaired. Use film probes where we have a more rugged requirement, where the environment is a little bit more harsh. However, the film probes will have a worse frequency response. It is electrically insulated and it is protected against mechanical and chemical action. So there is an advantage of the films, but then the wires are relatively inexpensive and it also has better frequency response. So depending on your need, the end application, you'll either go for wire probes or film probes. Okay, so this gives us another idea of the comparison between wire and film probes. So if you look at a 4 micrometer diameter hot wire sensor versus a 50 micrometer diameter hot film sensor, this is how the frequency response will look like. So you can see that we have a cutoff frequency of 90 kilohertz for a wire, whereas the cutoff frequency is reduced to around 75 kilohertz for a film sensor, right? So this is the amplitude versus frequency response for this kind of for different kinds of. So this you can see is a wire, and this is slightly thicker, or yeah, I mean you can see 50 micrometer diameter. So this is a hot film probe sensor. Okay. And then the types of, so where are these kind of anemometers used? So this is again to give you an idea and raise interest in you in the subject, that finally where does it go? All these discussions that we are doing, right? Finally, where will the anemometer sit, right? So these are used in, it can be used in windmills or, aircrafts, right? And these are the different kinds of flows that we associate with a flow meter or an anemometer, right? We have a laminar boundary flow, then we have a transition zone region, and after that, once the velocity increases, that's where we will have a turbulent boundary layer zone, right? And then, so these are the different flow types: laminar, turbulent, or transitional. Transitional is, of course, as the name suggests, it's somewhere in between, and most of the anemometers will end up detecting velocities somewhere here, because this is where we need to focus our systems on. We don't want to go into these zones, right? We will probably take corrective action before the laminar boundary flow itself gets I mean the flow. We don't want the flow to go from here to here, right? So so for motivation for boundary layer research are, of course, as I said, aircraft wings, wind turbines, turbo machinery, heating and cooling kind of machines with heating and cooling kind of requirements, wherein we have to ensure that the temperature is kind of maintained because of a fluid flow. So all these requirements kind of come into picture when you talk about anemometers. Okay, I think that kind of brings us to the end of the anemometer discussion. So any question up to this point? So the next we will look at inertial sensors. And shall we start this today, or shall we pause? Let me see. I think stop it here today, Shubham, because you're the only person attending, and we'll start with the inertial sensors in the next class. Right? Any questions, Shubham?
No, sir. Like I will go through the maths and.
Can you be louder, Shubham?
No, sir. Like I will go through the maths and then get back to you if any questions.
Yeah, and especially the way the feedback is taken, or actually an active area of research can be, all these Western bridge arrangements, right? So that is one thing that I did for my own PhD work. That was for an accelerometer, is coming up with a, different alternative structure of the Whetstone bridge. Actually, not use the bridge at all, but use some other mechanism to, let's say, measure the resistances and then do this convert the, the measured voltages, analog voltages to digital voltages, and then do signal processing to get rid of, different kinds of errors or non-linearities, whatever you call it, right? So that this itself is actually a pretty active field of research. Anyway, we stop here today, and then we'll start uh, the next discussion in the, the acceleration